In this video segment, we're going to talk about gravitational force. It has been well known since ancient times that Earth is a sphere, and objects that are near the surface tend to fall down or fall to the center of the Earth. Newton connected the idea that objects, like apples, fall towards the center of Earth with the idea that the Moon orbits around the Earth, is also falling towards the center of the Earth. The Moon just stays in a circular motion since it has a velocity that happens to be perpendicular to that acceleration. So it's moving fast enough that instead of falling into the Earth, it falls around the Earth. Newton concluded that all objects attract one another with a gravitational force. The magnitude of the gravitational force decreases as the centers of the masses increase in distance. So in the first example here, we see M1 and M2. They have a gravitational attraction due to the fact that they are some distance away. As we move their centers further away, a distance of r prime, that gravitational attraction becomes less. So the closer the objects are, the more attraction they have. The farther away they are, the less attraction they have. There is a proportionality constant that goes along with the law of gravitation. So there's a proportionality between the masses, and it's inversely proportional to the distance squared. The proportionality constant is called the gravitational constant. It's equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. In 1798, Henry Cavendish actually built a torsion beam balance. He did this in order to verify this gravitational force. He didn't initially set out to measure G, and in fact, he himself did not measure G, but people using his torsion beam did measure G, and that became the gravitational constant. And I will go ahead and click on the video or give the video link in addition to the lecture notes. Mathematically, the magnitude of the gravitational force decreases with the inverse of the square of the distances between the centers of the masses, and it's also proportional to the product of the masses. So the force, F1, is equal in magnitude to F2 because it's an action-reaction pair. This force is equal to m1 times m2 divided by r squared times the gravitational constant, which ends up being your proportionality constant. The direction of the force is along the line connecting the two centers of the two masses. Each mass feels a force of attraction towards the other mass along that line. So here we have force on ball 1 by ball 2 is equal in magnitude to force on ball 2 by ball 1. Notice again that these are pointing towards each other or towards the center. So if we were to actually write out the direction for this, we would again use negative r hat. Newton's third law tells us that the force on each mass is equal. That means if I drop a pen, the force of the earth pulling on the pen down has to be equal to the force of the pen pulling the earth up. Since the mass of the earth is so much larger, that force causes the pen to accelerate a lot more, while the movement of the earth up is completely unmeasurable because the acceleration is so small. So basically what we're looking at is the mass of the earth and its acceleration is equal to the mass of the pen times its acceleration. Okay, so the two forces are equal, but notice that the acceleration of each object is going to be different based on the fact that the masses are not the same. Okay, so now in these video segments, we're going to have some practice multiple choice questions. I'm going to read the question to you. You're going to pause the video, go ahead and select the correct answer, or at least the answer you think is correct, and then restart the video and I'll show you the correct answer and why. So for question number 1, what is the magnitude of the gravitational force between the Earth and its moon? R is the radius or the distance between the Earth and the moon. It is 3.8 times 10 to the 8 meters. The mass of the Earth is 6 times 10 to the 24 kilograms. The mass of the moon is 7.3 times 10 to the 22 kilograms. So again, what is the magnitude of the gravitational force between the Earth and its moon? Go ahead and pause the video now. Okay, so let's go ahead and take a look at the answer. The correct answer is C. You should have used F equals G m1 m2 over r squared. G again is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. What is the magnitude of the gravitational force between the Earth and its sun? The distance between the Earth and the sun is 1.5 times 10 to the 11 meters. The mass of the Earth is given. The mass of the sun is 2.0 times 10 to the 30 kilograms. And again, the force is G m1 m2 over r squared. And G, capital G, is equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Go ahead and pause the video now. Okay, so let's go ahead and take a look at the correct answer. The correct answer is D. Hopefully you got 3.6 times 10 to the 22 newtons. If you're finding that you're not getting these numbers correct, one thing I would suggest you do is make sure you're using the EE button in your calculator instead of using times 10 to the negative or times 10 to a power. What tends to happen is when you use 6.67 and then you use that 10 to the power button, if you don't put it in parentheses, you're going to end up getting the wrong answer. So if you don't have your parentheses nested correctly, it will get you the wrong answer. You can replace this here with the EE button, and then you just type in 6.67, you hit the EE button, and then negative 11, and that's how you would type it in. It actually takes a lot less time to do that as well. I'll go ahead and show everyone in class. The gravitational force between two objects is F. What is the force F prime between those objects when the distance between them is halved? Okay, this is a ratio problem. So what you're going to do is you're going to take F, and then you're going to divide it by F prime and see what the relationship is. Okay, if you haven't paused the video, if you need more time, go ahead and pause. Okay, so let's take a look. The correct answer is D. If the distance between them is halved, that becomes 1 over 1/2 r quantity squared, which ends up giving you 1/4 r squared. Well, 1 over something gives you something, so it's going to be 4 times greater. Now, let me ask you this. Does 4 times F make sense? Yeah, actually it does. Okay, if I'm moving these objects closer, right, I'm halving the distance. So if I'm moving them closer, shouldn't my force get larger? Yes, it should. So right away I can cross out A and B. So that only leaves me C and D. You may have chosen C because you forgot to square the 1/2. Okay, so don't forget that. It's 1 over r squared or 1 over d squared. The gravitational force between two objects is F. What is the force F prime between those objects when the mass of one object is doubled? Go ahead and pause the video. Okay, so let's take a look at the correct answer. Hopefully you chose C. If you double the mass, you double the force. The gravitational force between two objects is F. What is that force F prime between those objects when the distance between them is doubled? Go ahead and pause the video. Okay, so let's take a look at your answer. Hopefully you chose A, 1/4. If you double the distance, it's 1 over 2d quantity squared, which becomes 1 over 4 squared, or 4r squared, which becomes 1/4. Recall from previous courses, hopefully you remember this if you've had earth science. If not, hopefully you've covered density in a previous course. Density is written with a rho. Okay, so this may look like a P, but it's actually the Greek letter rho, and it's equal to the mass per unit volume. The volume is equal to 4/3 pi r cubed when we talk about a sphere. Now we can see what happens to the gravitational force between two objects when the mass, density, or the volume is changed. Because here, mass is related to the density times the volume, and volume is related to the radius of the object cubed. For example, let's look at the gravitational force between two spheres shown to the right. Since mass is equal to the density times the volume, we can rewrite the force as G times rho 1 times 3/4 pi r1 cubed times rho 2 times its volume, which is 3/4 pi r cubed, all divided by the distance between them squared. Well, the distance between the two centers is going to be here, R1 plus R2. So the distance between them is going to be R1 plus R2, and we're going to square that quantity. Two solid spheres made of the same material have radii r attract each other with a gravitational force F. The two spheres are replaced with two new spheres of the same material with radii 2r. What is the new gravitational force between them in terms of F? Go ahead and pause the video. Okay, now hopefully you refer to the equation we just went over, which is this one right here. Okay, so let's see what happens if we change the radii to 2r. The correct answer should be D. It should be 16 times greater. Two solid spheres made of the same material and radii r attract each other with a gravitational force F. One of the spheres is replaced with a new sphere of the same material with radii 3r. What is the new gravitational force between them in terms of F? Go ahead and pause the video. Okay, so let's take a look at the correct answer. The correct answer is C, 27/4 times F. If you're not getting these, go ahead and put a question mark next to them, and please ask me in class or go ahead and text me. In the next video segment, we're going to talk about gravitational fields.